So we're going to move from our entities and attributes to talk about how to normalize different relationships. So most of the relationships that we come across are binary. So there's just two entities connected by one relationship. And most of them are also one-to-manys. This is how the majority of your relationships are going to look. You can see that the primary key on the one side, which in this case is the customer, the one on top, has become the foreign key on the many side, which is in the order, and the line goes straight up, just like what we've been talking about. However, sometimes we have many-to-manys. There it goes. So if you hadn't done it before in our ERD stage, now you have to do your conversion for sure. And that is taking our many-to-many relationship, turning it into an associative entity. And so you're going to go from that diamond to the diamond with the square. What that's going to do is going to give you 3 tables altogether. So your order, your product, they're going to come together. And in this case, they named the order line. You can see the order ID and the product ID are coming together to form a composite key. So in this case, they chose not to do a unique, a new primary key for order line. They're just using a composite one. Totally legal choice, but it will slow down your database if you're thinking about scale. So what would be better is instead of that, of having that primary key for just the order line, and then in that case, that one would have the underline, the order ID and product ID would have the dashed lines showing that they are just regular foreign keys. Okay. One-to-ones. We didn't actually see a lot of these in our practice and discussion because they're a little more rare. Almost always when you see a one-to-one relationship, they're usually one side of it is the one and only one, and the other side is maybe one. You can have 1, you can have 0, whatever. So in this case, we're going to have those in 2 different tables as usual. The optional one is the one that will carry the foreign key. And then also here is the first time that we've seen where, and I'm saying this is a different type of diagramming, but that where it says in charge is where our relationship diamond is. Date assigned is in a attribute coming off of that. But here you can see that the date assigned actually got moved to be part of the table that has the foreign key. So the foreign key and any relationships going off of the relation, any attributes going off the relationship come down into that same table. Okay. Now, if this had been like awesome enough to turn into an associative entity, then we wouldn't have that shift, right? So this only happens when that one little attribute is hanging out by itself on the relationship and doesn't have its own table. And I know some of you are going to be like, oh my God, why did we spend so much time talking about how that, like which ones need to be on the relationship and not hang out with the table? I'm sorry, it's just the way it is. But without knowing where it goes, odds are you might have been wrong anyways. But yeah, it's diagrammed one way in the ERD, and then when we bring it to the schema, it's diagrammed a different way. Okay, so moving from the binary relationships to our unary or recursive relationships. Most of those are going to be one-to-manys, as usual, because one-to-manys are our most typical case. When you see these, the foreign key, which is manager ID, which is the same list of people as our employee ID, like they're not different lists of people. They're all employees. The manager ID just goes on that same table and it loops back to itself, which is not that different from the ERD, but now you just see you see it plain as day, easy to see. For the many-to-many relationships, these are a little funky. These actually turn into two different tables, surprisingly. Our item number and component number in the component table on the bottom, they're actually the same columns, basically. Component number was a randomly made new column name for this. But it's just they had to differentiate them because they're both the same. They're both foreign keys to the item number. And that's because of the many-to-many, right? So any item in the item number could be paired up with any item in the component number in order to make a complete record along with that quantity. And again, we see the quantity that was part of the relationship is going to be tucked down into the component table because that is the one that has the foreign keys. Here, again, we see that they've, this book tends to like to do the component keys, but we know that they are less efficient. Okay, mapping the n-ary relationships. These get a little hairy. So if you hadn't done it before, again, this is the time where you need to convert n-aries into being associative entities. Personally, I find them a little hard to think about without that conversion because this is the final form, you know, Transformers. It is the final form. So you can see it traced out between the each of the entities that was on the outside and the foreign key on the patient treatment associative entity. All of that should make logical sense. You see that there's the original associative entity had its own 3 attributes attached to it: date, time, and results. And so what they did is they added all that together on a table and they said, okay, so a patient needs to see a physician in order to get a treatment which has its own treatment code. So those 3 together, plus the date and time, means that no matter what happens, say they got a cold and they came back to see the same doctor for a cold again, but there's a different date and time, or maybe they went to the doctor and they went for a cold because they had a cold, but they also had to get a shot because they're going out of the country and they needed vaccines and stuff. So it's 2 different treatment codes on the same date and time. So that any combination, like, that's going to be a unique identifier. Yes, technically. Ideally, let's not do that though, because now you have 5 different columns all inside of this. So A, it's not going to be that fast anyways. We've been harping on this. This is even worse than all the other examples that we had. And what really makes it really bad is if this associative entity ever gets linked to something else, a relationship with another entity where it is the one-to-many. Because what happens? This 5-column primary key all needs to migrate to the other table. That is it, because primary key goes to the foreign key. And so you're going to exasperate how bad the slowdown is in order to get this. It is way more efficient just to make yourself a little patient treatment ID number and make the rest of them just foreign keys. So technically it's not wrong, but it's definitely not best practice. And we're going to wrap this up with a discussion of the supertype and subtype relationships. We just learned these last week with our EERD diagrams. And what we talked about in there is that each of those subtypes are actually going to be their own little tables. They share the same ID as the supertype. So what they've done here in order to differentiate the names is they've added the the H, the S, and the C that we saw in the little identifiers next to the D or O option. And that is how they are making the really, really obvious that they are different ID numbers, which is a nice thing. These are all one-to-one type relationships. So they're super simple, and the foreign key goes on the subtypes. And we can tell that by looking at the arrows. Nice and easy. All right, so that is how to normalize. As I said before, you need to do this as a stepping stone, this is how to create a schema from your ERD, and this is what we need to do in order to do our normalization. So practice this. You're going to need to be able to do this for your exam. And as a schema isn't part of your project, it's not one of the deliverables, but you'll need to do it as part of just best practice of going through the exercise of making a database.